we've got enthalpy, we've got entropy. How do we figure out the total energy of a system? There's two equations, two types of free energy we can work with. One, which we talk about but we'll never actually practically use, is what's called the Helmholtz free energy. Now the Helmholtz free energy is represented by the letter F. And it represents the sum of all the enthalpy and entropy of the system, but it does it under the situation where we have a constant volume reaction. So if we run this in a sealed container, this would be a situation where we would work with the Helmholtz free energy. And again, the Helmholtz free energy, if we ever say free energy, it's the total energy, which includes all the enthalpy and entropy contributions. The other form of free energy is the Gibbs free energy. And this is represented by the letter G. Now the difference between the Gibbs and the Helmholtz is that while the Helmholtz is a constant volume, the Gibbs is a constant pressure. So this is more akin to what we actually see in the lab. Most experiments you will ever run in the lab, we do it open to atmosphere. So it's always operating under atmospheric pressure. If the pressure builds up in the reaction, it just simply expands into the room. And so the Gibbs free energy is the preferred measure of free energy for most chemistry experiments. Now the relationship between the Gibbs energy, the enthalpy, and the entropy is the Gibbs formula. Delta G, change in Gibbs energy, equals the delta H minus the T delta S. Delta H is our enthalpy, delta S is our entropy, and T is our temperature given in Kelvin. Typical values for delta G, plus or minus somewhere between 25 and 800 kilojoules per mole. Anything beyond 500, you need to start kind of questioning what result you're getting, but this is not unreasonable, 25 to 800. So what does the free energy tell us? Well, if we look at electrons and electron filling diagrams, they're always trying to get a lower energy. Well, this is also true of molecules. What molecules really want to do is they want to finish with less energy what they started with. So preferably, we'd like delta G less than 0, so that our final Gibbs energy is less than our initial Gibbs energy. Reactions in which the delta G is less than 0 are what are called spontaneous. So a spontaneous reaction is one in which we lose this reaction would like to go to it if it can. Being that if we have reactants in products and they have a negative delta G, the reactants will go to the products, assuming there's no barrier. If there is a barrier, such as a high energy transition state or physical separation of the reactants, that's when we won't see the reaction occur. But if we get rid of the barriers, the reaction should proceed. If we finish with more energy than we start with, meaning our delta G is greater than 0, and our G final is greater than our G initial, these are what are called non-spontaneous reactions, meaning that the only way to make these reactions go is to make the environment so high in energy that it dumps into our system and forces it to go in that direction. And that's it for Gibbs free energy.